Hello, this is Lab 4 for Physics 2211. This lab is an application of extreme sports that use ropes. This is a screenshot from a video that was an excerpt of an extreme rope climber swinging back and forth on this rope from the arch in the rock. The rope moves in both directions, both vertically and horizontally, and acts as a spring. The objective of this lab was to use Tracker to analyze a video of a spring oscillating while swinging back and forth, and then use Python to create a code to represent a model of the motion. The data from Tracker is imported into the Python code to analyze the motion of the spring. I found that there was no energy change in the system and that the simulation shows a perfect system with a few overestimations of motion. This lab is relevant because it uses Newton's second law and the work energy principle to predict future motion. Some of the physics principles used in this lab are spring force, where the force of the spring is equal to the negative spring constant times L hat, Newton's second law, where the system is told to be the mass alone, where F equals ma, and then the work energy principle, where the system is considered to be the mass plus the spring plus the earth, and delta E equals delta K plus delta UG plus delta US, and it is equal to 0 since no energy enters or exits the system. The video from Tracker looks as follows. And you can see the motion on the right, both in the x direction and the y direction. I was given the mass of the ball on the end of the spring to be 0.402 kilograms, gravity is 9.8, and then the initial velocity was 0 because the mass was released from rest. Then, from the data I got from Tracker, I was able to do a few calculations to find the spring constant and the relaxed length of the spring, as well as the initial position. So to get the spring constant, I use the equation where t is the period of oscillation and t is equal to 2 pi times the square root of the mass over the spring constant, and I algebraically rewrote that to solve for k, and then I plugged in the values I was able to get from Tracker to find the spring constant to be about 9.8 Newton per meter, and then I used a few equations for spring constant to find that the force of gravity is equal to the force of the spring, and from there I was able to solve for the relaxed length of the spring to be 0.299 meters. And the spring force is acting in the opposite direction of the weight force as shown in the free body diagram. The work energy principle is the sum of the change in kinetic energy, the change in gravitational potential energy, and the change in spring constant energy, and the system is the mass plus the spring plus the earth, and there is no energy transfer into or out of the system, so you would expect the work of the system to be 0. Each of these equations is worked out below for the kinetic energy, the gravitational potential, and the spring potential. When the code is run, it looks as follows, where you have the spring moving and you have a few graphs below. And the initial data plotted in the beginning from what I calculated based off of the Tracker data, the spring constant, the relaxed length, the equations for the relaxed length of the spring, and then all those equations for the components of the energy principle. And then the spring force is put in here with Newton's second law, and you have spring force, and you have Newton's second law applied for the change in velocity and position in reference to predicting future motion, and then all of the energy changes with the delta value of the change is put here, where the delta is the final minus initial of each, and then you have a few points on how to graph them. The results of the graph show a graph of energy versus time, x position versus time, y position versus time, and then this is what the spring looked like as it oscillated. And then this was not able to be produced from my code due to an error, but I found what the graph should look like, and it is this graph where the energy versus time is that straight yellow line as I was given, and then you have the changes in kinetic energy and potential energy oscillating back and forth within the position graph. So what does this mean? The fact that this change in energy versus time graph is at 0 means that the delta E for the system is equal to the W, or the work of the surroundings, which was 0. which does satisfy the energy principle because that is what was predicted. And then the period of oscillation is different when calculated from x position data versus y position data. As you can see, my calculations for x position data was about 4 seconds, and for y position data, the period of oscillation was about 3 seconds. This is because the x position was based off of the pendulum motion, which was the back and forth, and then the y position is based off of the vertical bouncing motion, which, as you could tell from the video, the mass moved a greater distance horizontally than it did vertically, so it makes sense that the period of oscillation for the horizontal motion is greater. So in conclusion, the model was not perfect because of the assumptions neglecting certain forces and the overprediction of the motion, and then the energy principle was satisfied, however, so this does support the physics principles it set out to support.